All right, more exponential function applications. Population of the world in 2015 is about 7.3 billion people, growing at an estimated rate of 1.1%. Assuming the model continuous growth with a constant rate, what will the population be in 2050? And when will it reach 20 billion? Okay, so a lot of words there, but first thing we need to do is understand that this is a continuous growth problem. So we're going to assume it follows the continuous growth model, which looks like this. Okay, so my function then, I'll build my function right now. In 2015, the initial amount is 7.3. The rate is 1.1, so 0.11. And t is my variable, right? So to answer the first question, what will the population be in 2050? I just have to be careful, okay? So we have to understand in 2015, we're going to start our model. So the time there will be 0. So in 2050, then the time would be the difference in the 2 years, right? How many years, or another way to think about it, how many years have gone by since 2015? Well, that would be 35 years, okay? So that's all I have to do to answer that first question is evaluate my function when t equals 35. So 7.3 e to the 0.011 times 35. All right, and it's just a matter of plugging that into your calculator. The only thing you got to watch out for is that you raise e to that product of 0.011 and 35. So make sure those are in parentheses, or maybe you do that multiplication first and raise it to the power and then multiply by 7.3. And that should give you a value of 10.7 billion. Remember, this is in billions, so we want to indicate that. And maybe even write people. That's the answer to the first part. Okay, now, second question. What will the population be in 2050? Sorry, second question. When will the population reach 20 billion? So in this case, I'm giving you the amount. You've seen this type of problem before. And asking for the time. All right, so I got to solve that equation. So isolate your exponential expression. 20 divided by 7.3 is 2.74. So that gives me this equation. 2.74 equals e to the 0.011t. And at this point, we're going to apply our log definition, right? I need logarithms to solve this equation. So I know that if y equals a to the x, then the log base a of y equals x. So I got to apply that property to this problem, and I know that the exponent, 0.011t, is equal to the log base e, so the bases have to line up. Natural log is the natural base, and then I'm taking the natural log of 2.74. Okay, so the good news is we're given base e. When I translate it to log, it's the natural log, and that's on my calculator, right? So to solve this equation, I just have to divide both sides by 0.011, and that gets me t. So t is the natural log of 2.74 divided by 0.011, which if you plug that into your calculator, should give you a value of 91.6. Okay, so t is about 92 years. Okay, but now be careful because we want to answer the question. The question says when. So a valid answer would be after 92 years or in the year 2015 plus 92, right? Which would be 2107 is when the population would reach 20 billion. Okay, one more problem. You can see these are similar. Essentially, you're given an exponential function, and you're asked to either plug in t and find a, or plug in a and find t. Right? That's essentially what we're doing here. If you have to plug in the value for a, you need logs to solve. If you're just plugging in t, you're just running it through your calculator, getting the output. All right. So the amount of grams of uranium-232 is given by this function. right? So exponential modeling lends itself to the decay, exponential decay, and as we've seen before, exponential growth, right? So in this example, you want to know how much of a 100-gram sample is present after 250 years, right? If it's given by this formula, again, A naught is the initial amount. So after 250 years, I'm just plugging in 250 into my function, right? The initial amount for this question is 100. There's my decay rate, and time is 250. That's it. Very similar to the previous problems. In this case, you're given t and asked to find a. All right, so you should know that should be less than 100, right? Because of this negative exponent, if we were to look at the graph of this guy, it would be decreasing, right? Decay. So as time goes on, there's less grams. And if I plug that into my calculator after 250 years, and I'm starting with 100 grams, I should be reduced to about 8.2 grams. All right. Next question, what is the half-life of uranium-232? Well, what does that mean? What is the half-life? That should be, the answer should be time, right? Another way to ask that question is, how long will it take for the amount of radium to be cut in half, for half of it to be gone, okay? So how can I do that mathematically? Well, if I start with my initial amount, negative 0.01 t, remember I'm going to have to solve for t here. What should the output be? It should be half of the initial amount, right? If the initial amount is given here at A naught, then half of that is just half of A naught. Another way to do this problem would be to go ahead and put your 100 in here for A naught if you want. And over here, what's half of 100? It'd be 50. Okay. Either way you do it, the next step is to attempt to solve for t, right? So I know this looks a little confusing because I have what appears to be a bunch of letters, right? But remember, I only have one variable, which is all we're solving for. The variable is the t. These are fixed values. We know what e is, right? So the step to isolate my exponential expression will be to divide by the A naught, right? So that would go away there, that would go away there, and essentially we'd be left with the following equation. 1/2 equals e to the negative 0.01 t. Right? And like I said, if you wanted to put in 100 here and figure out what half of that would be, which would be 50, you divide both sides by 100, and you still get a half over here. So if you don't like this way, just pick any value you want for the initial amount, and essentially you're going to get half of it. Okay. So at this point, we've seen these a couple times now. This is an exponential equation, base e, and I'm asked to solve it. So I have to translate that to the logarithmic equivalent. So it's going to be the exponent, negative 0.01 t, is equal to, same base, in this case the natural base, natural log of 1/2. Divide both sides by negative 0.01, negative 0.01, cross that out, and that's my answer right here. But I just want to give that, I want to run that through my calculator because it doesn't make sense to say the natural log of 1/2 divided by negative 0.01 years, right? It would make sense to give what that value is, and if you plug that into your calculator, you should get about 69 years, giving you the half-life of uranium-232. So I'll write that over here, 69 years. And that is the half-life of uranium-232.